Hi all, welcome to CircuitSutra's presentation on CST Qemu. This presentation is about using Qemu in SystemC based virtual prototypes. To start with, I will be discussing what is Qemu, its advantages, and how we can leverage Qemu's matured CPU models and its reference ports in our SystemC based design and verification flows. This would be followed upon with few case studies or examples. What is Qemu? Qemu is an open source processor emulator and can be freely downloaded from www.qemu.org. Qemu is a fast open source processor emulator available and its performance is very close to host machine performance. Qemu is able to achieve this by dynamically translating guest instructions into host machine instructions and running them on host, thus by decreasing the boot time and runtime of the applications running on the simulated platform. Qemu is completely implemented in C language and have its own simulation engine. Qemu supports various CPU architectures, ARM, Microblaze, PowerPC, Spark to name a few. Also, by following Qemu's certain guidelines, one can either add a new CPU architecture or can enhance features of the existing CPU models available with Qemu. Apart from the CPU and IP models, Qemu also have various reference boards which one can readily use to bring up a SoC and run either bare metal application or full-fledged OS. As we are aware, SystemC is a standard language for modeling SoCs and electronic systems. It is becoming a language of choice for SoC companies and electronic system companies to develop virtual prototypes of their SoC and electronic systems. SystemC, being a standard, allows interoperability of models from various third parties and can simulate them in popular virtual prototyping tools. Now, the natural question arises: can we use the rich Qemu infrastructure with SystemC? By default, the answer is no. All the CPU models or IP models or reference boards available with Qemu are all implemented in C language and use Qemu's simulation engine. It does not interoperate with SystemC simulation engine, ports, interfaces, signals, events, etc. Hence, Qemu does not fit with the SystemC based design and verification flows. If somehow we can enable Qemu's infrastructure to be used with SystemC, it will provide a huge value addition. Lots of models or reference boards can be readily used without having to develop everything from scratch. How do we enable this integration? The answer is to extend Qemu with SystemC. We have developed CST Qemu by developing a SystemC or TLM 2.0 wrapper over Qemu. Here, by extending, I mean exposing Qemu's interfaces, importantly CPU's bus access interfaces as SystemC interfaces. Similarly, establishing proper interconnection between SystemC signals and its corresponding Qemu API calls. And most importantly, synchronizing SystemC simulation engine with Qemu simulation engine, as we are trying to co-simulate both as one VP. We have implemented two ways of synchronization between Qemu simulation and SystemC simulation. User may choose to synchronize after execution of every n number of instructions or at a certain time quantum. Actual value is configurable. If we choose higher interval between two consecutive sync, then simulation would be faster. However, there are chances of some critical events being missed, and we have to compromise on the accuracy. On the other side, lower interval means higher accuracy and slower simulation. We need to choose the optimal value depending upon the requirement of the use case and the kind of software that we intend to run on the virtual prototype. Another important functionality in the wrapper is that you can specify what all address space will be accessed from within Qemu and what all will go out to the SystemC world. This functionality allows users to use the existing reference boards from Qemu and connect the external SystemC models at backend address spaces. Apart from extending with SystemC integration, we also have implemented some useful features in Qemu. We have extended the built-in tracing feature of Qemu to implement an advanced CPU instruction tracing feature which, when enabled, dumps logs which are easier to debug and compare while running automated test suites. Debugging embedded software is done through Qemu's integration with the GDB client. and it works like a server client mechanism with VP running a GDB server in it listening at a particular port number. Debugging can either be done through a command line interface or using Eclipse GUI. For customers, we also integrated Qemu with their specific debugging tools or environment. We can also implement the integration with any other debug tool if we get the API interface of that tool. This above discussed methodology of extending Qemu with SystemC is successfully deployed by several customers in their production environment. Here is an example VP based on CST Qemu. In this, we have used ARM Cortex M3 ISS microcontroller CPU model along with NVIC model from Qemu to integrate with other CPU, other SystemC or TLM 2.0 IP models. For this particular setup, we have developed SystemC models using CircuitSutra modeling library, shortly CSTML, and VP Quick Start package or VP QSP from CircuitSutra. However, customers can use any modeling tool or library which is compliant with SystemC or TLM 2.0. Here, VP is platform independent, that is, it can run on Windows, Linux, 32-64-bit machines. Also, as it is compliant with CSTML, the VP itself is tool agnostic, that is, it can be integrated with any other VP tool to leverage tool specific features without core model code being altered. One of the important use cases of such VPs is automated unit testing of firmware. Typically, such regression setups are invoked from command line or script. Basic flow would be as follows: cross-compile C or assembly test case with appropriate tool chain. Invoke the VP by enabling all or required logs, namely CPU instruction tracing logs, embedded software logs via semi-hosting option, hardware or VP logs. Load the binary into memory and run the VP until the test case exits or till a timeout period. Compare the logs generated with golden reference logs to come out with a pass or fail result. One can also run VP with various quality validating tools to assess and maintain firmware quality throughout the lifecycle of the product. Here comes a little more complex VP with respect to the one shown in the previous slide. Here, VP is based on Qemu ARM Cortex A15 CPU, again extended using SystemC as discussed in the previous slides. Apart from the CPU model, all other peripherals are SystemC and TLM 2.0 based models. Again, these models are developed using CSTML and VP QSP, and this VP is capable of booting Linux. This VP can also be used for embedded software development. This is one of the reference board Xilinx Zing 7000 available inside Qemu. This reference board is implemented by Xilinx and is capable of booting Linux. This reference board uses Qemu's ARM Cortex A9 MP core with several Qemu based IP models. Address space and IP connections of this board are configurable through a device tree source or .dtsi file, which is compiled to a .dtb or blob file and provided while bringing up the board. As we know, Xilinx Zing 7000 is a FPGA SoC which have a fixed SoC with specific IP and CPU, and it also have a configurable FPGA in which users can implement their own design IPs. This reference board inside Qemu represents the virtual model of the fixed SoC portion of Xilinx. More details can be found in the URL given in this slide. We used CST Qemu mechanism to enable integration of SystemC or TLM 2.0 models of additional IP blocks with the Xilinx Zing 7000 reference board. For the design IP that intend to go in the FPGA portion of Zing, users can develop SystemC models and integrate with virtual model of fixed SoC portion that comes as a reference board in Qemu. This gives us the extendable virtual prototype of Xilinx Zing 7000. It can be used for firmware development and testing of additional IP. If the customer is implementing the design using SystemC high-level synthesis, then this VP can also be used for functional verification of these HLS designs. That's the end of the presentation. To summarize, we saw how we can use rich Qemu's infrastructure in SystemC based virtual prototypes along with few examples. Thank you.